So it's a pleasure and honor. I mentioned him earlier, and I'm happy to introduce Gianluca Antonelli. He is a colleague from the University of Cassino, that it's between Rome and Naples for the non-Italians. And he will talk about robotic manipulation, inverse kinematics, and motion planning.
Thanks a lot, Giovanni. From the last line, can you raise your hand if you hear me? Yes, okay. First of all, I would like to thank the organizers for inviting me. This is more or less the 10th time that I come here in Lecce, and it will not be the last because it's a town, really, it's a region that I love. Then I would like to criticize Giovanni because Cassino was not in the map that he showed. I mean, there were Grosseto, Forlì, Lamezia Terme, but not Cassino. I mean, that's quite insulting. By the way, my name is Gianluca, and it's a pleasure for me to talk about inverse kinematics and a little bit of motion planning, basically inverse kinematics for redundant robots with focus on mobile robotics in the framework of Industry 4.0 as, I mean, the topic of this summer school. I'm going through more or less those topics. As I said, basically, I'm going to discuss about kinematic control, and I'm going to show again the control loops that Giovanni showed earlier, a little bit different, because we organize the topics together with Enrico that will talk after lunch. So in next 2 hours, we will stay more or less in kinematic level with a little bit of motion planning. So going very quickly, mobile robotics, everything we are going to see in the next 2 hours will apply to structures as the one that you see here. And for example, this robot here, manufactured by a Canadian company, Kinova, exhibits 20 degrees of freedom. We have 2 of this one in our lab. The 2 arms are 7 degrees of freedom each. Then the base is 3 degrees of freedom. It's fully controlled because possesses Swedish wheels. And then there is also a prismatic vertical joint and pan tilt RGB. So quite a lot of degrees of freedom we want to be able to control. Okay, all the others more or less exhibit a similar number of degrees of freedom. However, what we are going to see has been applied as well in apparently different robotic structures. From the kinematic aspect, they are actually very similar, such as, for example, aerial, underwater, spatial. This is humanoids, but with wheels, snake-like, and so on. The examples that I'm going to show you will stay at more industrial level, so robots ground with mobile base, okay, indoor robots with mobile base. But there is plenty of literature of the same algorithms extended to other structures as those one. This is the same architecture that Giovanni showed earlier. Is a little bit more colored, and it has one loop in addition to that of Giovanni. This is just because those are, I mean, purely functional. I mean, then you can have a lot of different implementations and a lot of different nomenclature in the literature. So basically, we have a robot. The robot interacts eventually with the world, physically, possibly. We are not going to talk in this next 2 hours about whatever is here. That was navigation in the loop of Giovanni. In other textbook, you can find this as localization, for example, or I just used the word estimate. So whatever is here, nonlinear Kalman filter, for example, gives you all the information you need about the robot configuration and everything around it that may be useful. Okay, this is the purpose of this block. And then we have 4 loops here, and high-level loop, decision-making, for example, or scheduling, as said Giovanni earlier, that provide a inner loop with the goal of, let me say, a mission or something to accomplish by the robot. With still with, for example, an high-level description. So bring a bottle, for example. This is the goal. Here, in the yellow loop, I just put a motion planner, and we can imagine that here there is a stochastic or random-based motion planner that still works at the word level, so the Cartesian level. I need to bring a bottle. I need to develop a trajectory for my end, so only for the end, for example. And so the output may be the end effector, ignoring all the remaining, for example, or not. And here we have an inverse kinematics control loop, which transform the Cartesian plus a lot of other control objectives we will see later into, well, Q is the configuration, the desired configuration of the robot, so the desired position at each sampling time. Okay? And we will focus our attention here. Then the control loop, the red one, is a controller that provide the torques or force to our motors, basically. And finally, we are in. The frequency at which those loops needs to work is higher from left to right, from outer to inner. For example, if you need to implement interaction control, current hardware for a torque-based controller goes from 2 to 1 to 0.5 milliseconds. Okay. However, an inverse kinematics in industrial robotics can be implemented also with a sampling time of 10 milliseconds. And if you are in an environment with a much lower bandwidth or underwater, here you can also run your kinematic controller at 1 hertz, at 1 second. It depends from the bandwidth of the desired bandwidth of the, and so on. We are going to make, so this is a focus only on the few inner loops, input, control objectives, generic. We are going to see a little bit better what are those control loops now. But we are going to make this assumption, basically, that the controller is perfect. So basically, we are ignoring the presence of the control, and the output of our inverse kinematics, we assume that is exactly the output of the real robot. Okay, this is the basic assumption that everything you ask can be done, but we will put the constraints in the control algorithms. Just few slides to define the variables, the names, and we will use the letter Q. Okay, this is a ground Fritzer robot. Usually in the textbooks, the letter Q is used. Okay, so for the differential level, usually we use the letter J for the Jacobian and V for the end effector. Actually, we know that there are two kinds of Jacobian, the geometric Jacobian and the analytical Jacobian, and V can be both the linear and angular velocity or the time derivative of the orientation representation. So if you add a introduction to robotics class, you may find some, let me say, abuse notation that is a nice way to say there are some errors. Those are intentionally because I decided to keep the notation as simple as possible. And sometimes this will, the price to pay is that some equations will be a little bit wrong, okay? It was intentional. For a robot with a mobile base, we do have the linear velocity of the base, the angular velocity of the base, and the time derivative of the joint positions to take into account. So my system velocity actually, let's say an underwater robot is 3, and n, or a mobile robot is less. And the Jacobian is not only function of the configuration, but also the orientation of the base. Okay? We need to take into account this, but as I said earlier, for me, from now on, Q will denote the base Q joint configuration, only the letter Q, okay? And Q dot will embed base plus joint velocities in order to keep, there will be some equations, okay? So Giovanni had a high level presentation, and we are going a little bit on the equations. But in order to keep it simple, let me, from the notation aspect, let me use Q dot for velocities, also the base velocity. The dimension of Q dot depends on the base. We can have 2 for additional differential drive, one linear and one angular, non-holonomic, as Giovanni introduced earlier, or 3 if it is omnidirectional, 2 for the linear velocity and 1 for the angular velocity, 4 for a quadrotor, because quadrotor you don't have full control of the orientation, up to 6 for certain kind of underwater base. Again, nomenclature, we will use the letter sigma as a generic control objective. So sigma may be, for example, the position of the end effector. Basically, this will represent the differential mapping from the system velocities to the time derivative of the control objective by means of, well, let me say appropriate Jacobian. Okay, so abuser notation. It's not totally, it won't be totally correct for all kind of structures, but it will help us to keep simple some of the equations that we are going to see. We are not going to use the dynamics, just for sake of completeness. This is the classical equation that you may have seen in an introduction to robotics class with fixed base, so classical first robotics class. For mobile robotics, formally, the equations in matrix form are the same. Of course, there are a lot of differences within the kind of sensors in order to acquire, of course, the information. And the properties, if you go in a fluid more dense than the air, such as the water, for example, the properties may change a little bit. You may have also the buoyancy, and so on. We will skip this one because we'll stay at kinematic level for next minutes. Okay, what do we want to control? Very briefly, let us see step by step some of the control objectives that we may want to control. Basically, we have in hand, and we may decide to control the position. So let me say, we fix 3 degrees of freedom of the system, or position orientation, 6. But we may also want, for example, to control only the distance from a point or from a wall or whatever, or we may want to align the direction. If we have a directional sensor or a camera, in such a case, we only need 2 degrees of freedom. Some kind of optimization-based control objectives, such as, for example, the joint limit. There are several examples in the literature. This is one possibility. I'm not going to the equation, of course, but what is important to notice is that I may want to control something related to the robot configuration. This is again related to the robot configuration. I may want to control a matrix that tells me how close I am to a kinematic singularity, so when the rank of the Jacobian decreases, and if I can, to avoid to go in a kinematic singularity. And one possibility is basically the determinant of JJ transpose, because this is an information. If it goes to 0, I'm in a kinematic singularity. Whatever related to the base, of course, can be, again, the distance or the position or the orientation. So for example, I want to control the orientation such that my pan tilt camera is aligned with the scene where I'm working. And I need to put it explicitly in my control task, of course. If I want to control this case, this is a CAD view of the MobRob. And if I want to bring, we will see a video later on. If I want to bring an SL on a desk, I need to explicitly tell to my algorithm, look, it's better if you go in that position rather than in that one, because, well, the pan tilt camera here is looking on side of the scene. So I want to be able to consider control objectives at the same time. Vision space, if I want to control image plane, sorry, if I want to control features in the image plane, I have a control objective together with a Jacobian. So everything looks more or less the same. Specific cases as the underwater one or the center of mass of humanoids for working reasons. Whatever is something that I can put in a sigma function and I want to control, and we will do in next minutes, we will review some algorithms in next year. Then, if you look in the literature, you can find a lot of fancy definitions, and here there are some that I just read, such as safety, cohesiveness, repulsion, survivability. Well, from the mathematical aspect, more or less, we have covered, the task's objectives. So only different label attached to the same mathematical function. Let's see the general solution. And this is something that I assume that most of you have done because we saw your background. So I assume that most of you have a introduction to robotic class or even more. I want to invert the mapping. So basically, this is my mapping I want to invert. And we will assume that this is a Jacobian with more columns than row. So from the mathematical aspect, this is a set of linear algebraic equations. And we know from the theory of linear algebra how to invert this one. Okay, so we will, let me say, fit the linear algebra theory to the robotics interpretation or robotics point of view. We want to make the inverse mapping. Okay, from sigma dot, we want to see what are the velocities that provide me with the desired sigma dot. Solutions that we see as first solution in robotics classes. I have infinite solution. So I can, for example, I can design an optimization problem where I minimize a weighted norm of the system velocities subject to, well, the equations that needs to be satisfied. And this is a well-known mathematical problem for, I think, a couple of centuries that can be solved, for example, in closed form with the least squares. Okay, this is a weighted least square where W is a weight matrix that should be positive definite that can weight the different importance or cost of moving one joint rather than another. Of course, here Whitney 69 is written. It is not the first author that came out with a pseudo inverse, but is the first that came out with a pseudo inverse in robotics community. Okay. Okay, then if I don't want a minimum norm solution, another possibility is that, say, I give you an arbitrary Q dot A, can be assigned in some other logics, and I want to find the solution that satisfies as well the constraints of the differential kinematics, but is as close as possible to this arbitrary velocity vector. In such a case, the solution also includes the null space projector. So basically, the first part is the same. There is not the weight, just to have a little bit more compact the equation. And this is the pseudo-inverse seen in the previous page. Q dot is equal to pseudo-inverse sigma dot plus then the arbitrary vector is first projected into the null space of, in this case, this is my constraint, so it's my control objective. Okay, and this is the general solution to our problem. From now on, we will consider sigma dot as embedded also the closed loop. But in the equations, I'm only using sigma dot, just to keep it simple. But the closed loop will be here. Okay? Basically, Q dot A can be used, for example, to optimize something. Now, this is a robot with 7 degrees of freedom, manufactured by KUKA, is a German company, but I think now the owner is Chinese. If I control position orientation of the end effector, I only fix a 6 degrees of freedom system. And actually, I have infinite solution up to the mechanical joint limit of the joint. And I can use this in order to do something. For example, we will see later on, optimize something. So basically, this is a commercial video, but expresses very well the concept of internal motion. If I fix position orientation, my arm still has 7 degrees of freedom. I can move a little bit my internal motion, my shoulder. And this is what happened with the robot. And of course, I mean, this is a commercial. The wider and the better, because it means that you can do a lot of internal motion to do something else, to reconfigure, for example. Okay, close to a kinematic singularity, what can I do in order to avoid to invert a low rank matrix, which will provide infinite joint velocities or a division by zero error? Well, I can design a different control objectives where together with the norm of the joint, I also put the error, so a new concept, the error. In such a case, with a certain scalar compromise factor, I come out with the damped least square, where I have these terms that numerically regularize my problem. However, the price to pay is that I have a certain error. So I can play and can balance the need to have a small velocity and to avoid a too large error. This is the basic solution, and probably, I mean, the textbook stops here for a master degree. However, there are a lot of more advanced solutions, such as, for example, SVD-based filtering that avoids some of the issue with this one. What is the problem with lambda? Well, the choice of this lambda should guarantee 4 constraints or 4 features. We want to avoid the presence of chattering. Why? Well, lambda is if I change from the optimization of the problem and the introduction of the damped, I have a discontinuity. So if I don't design problem in my algorithm, I can chatter between the two solutions. I want to keep a small error, so I want tracking precision. I want to avoid to have too small velocities, because otherwise I'm not using my machine at the best of its possibility. And I want to have the same lambda for all the workspace, okay? So those are 2 examples taking the literature. I've canceled here the label because they're just as an example. If this is the minimum singular value of the Jacobian, and going to 0 means going to the kinematic singularity, I can decide to a certain point to introduce lambda with continuity up to a certain constant lambda when I'm close to the kinematic singularity. However, it's very difficult to tune the algorithms that handle the lambda. For example, in the end of a study, we weren't able to find it. Means that the best of our solutions still is trajectory dependent. In some place of the workspace, some parameters worked and some other not, and we were not able to find a magic set of parameters. Okay, what is the geometrical meaning of the null space? If I have sigma dot is equal jq dot with one equation and two velocities, well, basically, this is the equation of a line in a space where I have q dot 1 as x-axis and q dot 2 as y-axis, okay? So the solution of this one, this is a line. What does it mean? That the solution are all the velocities belonging to this line. For example, this line here. And the solution is this arrow here. This is the image. All this line is the image of the set inverse of the Jacobian. And the null space is, by property of matrices, is the orthogonal subspace. In this case, is another line, but because this is I mean, the only one that has a nice graphical representation only with two degrees of freedom. Okay, I don't care only controlling one task at a time. I want to control several tasks. I have 20 degrees of freedoms with my model, so I want to control several stuff. Several stuff means, okay, A is one task, but I want to add a B task. What's the problem? The problem is that the same system velocities will affect both A and B. Clearly, if I have position of task A and orientation as task B, if I move my joint, I'm changing both position and orientation of the end effector. So I want to be able to control several tasks at once. For example, this is our lab, and the robot is approaching the bottle. What do I want to control? End effector, the other end effector. I want to avoid to hit the table. I want to avoid to hit with the shoulder, with the base, and so on. So basically, I do have a lot of control objectives, and I want to control all of them at the same time. This is just a nice picture from the PhD thesis of Alexander Dietrich, the researcher at the DLR. I think now, I think it's senior something. He's not anymore a young researcher, but it's very nice because he started giving the idea of prioritizing the control objectives. This is very important. This is less important. But, well, very important, everything related to safety. Physical constraint, yes, a little bit less important because it joint limits, if I hit the joint limits, I just stop the motor with a line of code. So it's not, yeah, I stop the mission, but I don't hurt anyone. Well, then there is the reason why I'm moving the robot, so my task execution, and lower optimization. If I have something that I want to optimize, but I put it as lower. In the literature, in order to handle several control objectives, we start with similar works, really, I mean, back in time. Here, the citation is from the chapter of the handbook of robotics that Giovanni showed earlier, because it's the place to read first if you want to study a new topic in robotics. And the authors are Stefano Chiaverini, that belongs to my university, but also Giuseppe Oriolo, that will give a lecture tomorrow morning to you at 9, I think. So basically, just put some constraints, and in order to have a square Jacobian to work with, really a preliminary solution, or to augment your Jacobian, just put other control objectives, okay? In this case, we are putting other control objectives at the same level of importance as the reason why we are moving the robot. So those are still solutions that are a little bit naive, or can be improved, let me say. Then task priority redundancy resolution. Back in 85 or more, 87, 85. The idea is to have a priority, a strict priority between two tasks. And the second task is projected on the null space of the higher priority task. From formally, this is the solution, but it's not very important, I mean, the formal aspect. What is important is that I'm assigning a priority. The higher priority is always fulfilled if, I mean, properly designed. And the lower priority is fulfilled whenever it's not affecting the higher priority. Okay, so this is, I mean, this was the very first time this revolutionary concept has been introduced. I can introduce as much tasks as I want. For example, in this case, if I have 3, in a recursive way, I first compute the first one, the second one, and then the overall system velocity. I just have to pay attention that every time that I add a task, the null space should be the combined null space of all the higher priority tasks. Okay? And so this was, I mean, one possibility. Another is called singularity robust. The singularity robust has the same idea. I want to control 2 tasks in priority, but it avoids a issue with task priority that we will see a bit later, and is a more compact expression. And it's not very important, but what is important is that, again, I project everything in the null space of all the higher priorities taken together. A very popular control scheme is the hierarchical quadratic programming. So exploiting the quadratic programming theory in order to solve inverse kinematics for robotics. I'm going, I mean, a little bit fast, but this is the problem that I want to implement. I want to minimize a certain, the name for the people from the optimization theory is a slack variable. But let us look at this one as an error, because basically, if this omega A is 0, I have satisfied the equation. Okay, I want to minimize the error with respect to 2 variables, the error and the joint velocity, with a certain weight that is always positive definite. This is the first problem. If I'm lucky, the error is 0, and I go back on the second QP. In each sampling time, I'm solving all those QPs, but the current hardware allows to do it in 1 millisecond, so in the sampling time that is required by the current technology. So order of less than milliseconds for higher degrees of freedom systems. So the computational issue was a problem when it was first proposed, but now it's not anymore really a problem. So the second QP is, okay, the first task has been solved. And so you have this one as constraints, where now you use the number that came out from the first. So for example, 0. And this is a constraint. But now I minimize the error on the lower priority task. If I'm lucky, this is also 0 if they're compatible. But what is important is that this is now a constraint. And finally, I minimize Q dot with both given as constraints. Okay. Mathematically, I got the same results as the task priority within certain conditions, but for reasons that we'll see, I mean, in a few minutes, this is more used and more popular. Okay, those are the basics way to solve several tasks at a time. But if you look in the literature, you can find a lot of a large part of the literature that consider the tasks with a slightly different perspective. So they call it as behavior. And for example, what is a behavior? Well, a behavior is something that is really mathematically the same as a task. I want to control a certain variable. I define a behavior, whatever mathematical tool I want to use, and the output is a certain movement required to my system. For example, bio-inspired behavior, I want to reach the source of food. It means that I want to go in a certain place, okay? And so the output is a direction. If I have all those behavior, all these blocks are behavior, the input are sensor and control objective, then all the behaviors asks for a certain velocity. I need to combine all those velocities required by all those behaviors. And so, for example, normalize, and then combine with some weight, here there's some weight, normalize, and give it to the controller. Well, this is exactly what we have done with the task priority, with a different perspective. And we will see what are the different behavior of the system, so the different output of the system in very simple case studies. Okay. Quickly, why do we need a singularity robust task priority? Very quickly, because it's just geometry. Left-hand side with the E is the task priority, let's say the exact task priority. Right-hand side is the singularity robust. Here I have the only case that I can draw. So two tasks, each of one dimension, and two joints. So Q.1 and Q.1 and Q.2. Red line is the higher priority, blue line is the lower priority. Now, the red arrow is the solution of the sole higher priority. Blue arrow is the solution of the sole lower priority, if they were alone. Okay? The exact solution goes here. It actually finds the only point in the space that satisfies both the tasks, while the singularity robust, by means of a projection of the secondary into the null space of the higher priority task of the primary, as a solution. If you look here, this is far from the blue line. So I'm introducing an error on the secondary, which mathematically could have been avoided. But this has a positive value if you consider when the two tasks are almost, in this case, parallel. It means that if I take the two Jacobians together, they are almost rank deficient. With the task priority, my solution goes to high velocity, and I can avoid it by properly use a damped least square. With the robust, I keep the overall velocity small, so the amplitude of the solution here is small, and this goes to infinity. Okay? In both cases, I can handle this problem, but here I need to play a little bit with the damping. Here, I don't have to play, but I always have a larger error in the secondary task. And basically, when they are really parallel one each other, here you don't have a solution. You have a division by zero, while here you do have a minimum norm solution. So both cases you should pay attention when the two tasks are compatible alone, but not together. Not together means if I put the two Jacobian, one on below to the others, I do have a rank that is less than the sum of the two dimensions. Okay. The evolution of kinematic control now meets the last aspect, the introduction of the so-called inequality constraints. So basically, 69, this is what we have seen first. Then Liégeois, 77. We haven't seen this one, but this is in textbooks. Basically, you use the null space projector, and here you don't really have a secondary task. You have a gradient optimization of a certain function. Okay, this was proposed in 77 by Liégeois. Task priority, we have seen this one. Singularity robust task priority, more than 20 years ago. Multiple task priority, we have seen it. And then, okay, you have seen also this one, multiple hierarchical task priority, multiple singularity robust task priority, and then inequality constraints. Actually, inequality constraints means that my control objectives is not anymore a point. If I want to avoid to hit this wall, and I need to describe in words the control objectives, for example, for the end effector, I just say you need to stay, I mean, that direction from the wall, 10 centimeters far from the wall. So my control objective is in this axis, it stays from here to infinity. So basically, is inequality constraints or a set-based control. I want to stay in a certain set. Joint limit. If I know that my joint is limited from 10 to 45, I mean, I just need to keep it in this value. I don't want to assign to him a certain value. A very popular way is to adapt the QP approach in order to include also the inequality constraints. And for example, a contribution to this theory has been done also by the group of Genova, by Enrico that is here. The formulation basically has been proposed by a group of Mansart and Toulouse, and at the best of my knowledge, this is currently the most used approach to control high degrees of freedom robotic system. Okay, there are plenty of libraries that allow you to implement. There are several QPs in a hierarchy. You have to run several QP for each simple time. Okay. It's also powerful because it's easy to adapt to second order, so acceleration. I mean, we haven't treated, but you can also write acceleration kinematics, but also to the dynamics, so the operational space task priority approach. Even so, we haven't treated for lack of time, but a large literature is based on implementing task priority with the dynamics in the equations, starting from the work of Sama Khatib, 87, and then there are several groups. For example, currently, the group of Christian Ott and Alexander Dietrich are really working a lot in this domain. Plenty of libraries. Okay, the only issue is that some of them are maybe slow because they are not optimized. But I mean, if it's your topic of research, you can easily find also optimized code in whatever language, no? From MATLAB to C++ to Python and whatever. I mean, I never implemented this. Before coming here, say, okay, but if I talk, I need to implement it. It took 10 minutes in MATLAB to implement. Okay? It's not optimized, but. And then also set-based is the same. That is a work that we have done from Casino with colleagues in Norway by using the discontinuous switching dynamic system theory in order to prove convergence of the overall problem. So basically, this is a graphical representation of what I say. This is a wall. Here, I don't care about the position of this is the position of the robot, I don't care. And here, I need to take into account. And so add an inequality constraints that should be considered together with all the others. So basically, if I have a robot, mechanical joint limits, obstacle avoidance, directional sensor, manipulability, those are all set-based or inequality tasks, because I don't want to control a numerical value. I want to control a range. And some of them are critical, and some of them are not critical, so optimization. So basically, also the inequality should have a position in my hierarchy, okay? And a common way to classify the control objectives is according to, let me say, those three categories. You have priority, higher priority, everything is safety related. Then middle priority, mission oriented, and lower priority optimization. And for example, manipulability, field of view of directional sensors are optimization. I've shown you the theory, okay? But now all the videos are made in our lab with some of them. It's not important, the specific, because this lecture has a educational shape. So I'm showing this one only because it's easier, I have in my hard disk, but it's not important the specific kind of priority we implemented. Right? It's our, but it's not important. It's just important as an example. So this is Paolo that is going to interact with the robot that has all these control objectives that are embedded. RegBD is computing the skeleton of Paolo. And for safety reason, the robot is retracting. And also, it shouldn't go away from the, I mean, there are also some virtual walls that sometimes are drawn in the video, okay? So this is an implementation of multiple task priority with inequality, with set-based, in a 7 degrees of freedom robot. Okay, similar to the previous one. Okay, there are some control objectives in priority. Some of them are set-based, some of them are equality, and this is the labeling that you have seen, the classification that you have seen. Okay, now, I mean, this video is not, I think it's not very readable, but here, my desired path is the dashed red line. And due to the constraints, my actual path is the blue line. So I'm deviating because at a higher level, the safety task avoid that I hit mechanical joint limits. And the position is at the lower priority. So basically, I'm doing my task with a large deviation because of physical constraints. And then we do the same, but we also add the optimization task at the bottom for, in this case, to maximize the distance from the mechanical joint limits, because those were the constraints that were active during the movement. And now we only have to look at the blue line that is much closer to the dashed red line, because it means that by exploiting also the optimization, even if here I only have 1 degree of freedom. No, I think we are controlling only the position, not the orientation, yes. So here we have a null space of 4 dimensions. It's quite a lot. The same applied to the overall system, holding a tray. I didn't discuss about cooperation, about interaction, Enrico will do, but within the same framework, you can also include those aspects. We did it in a European project together in the underwater environment, interaction control within a task priority. Now, this is a graphical rendering of a numerical simulation where I only have the position orientation, basically, okay? And of course, without considering all the degrees of freedom, something bad always happened. For example, here, you can see that mean, there is a self-hit, so that the arm enter into the case. So this is not physically possible. So we do it, we run it again by considering the joint limit and the virtual wall as higher priority task. And this is the experiment in the lab. Sorry, it's not very fluid, I think, here. I don't know if here is a fluid or a video. Ah, no, ok, qui lo vedo a scatto. And this was, no. Now also with the base optimization, so the orientation of the base in order to optimize the sensor positioning, so the RGBD with respect to the scene, so with respect to the desk. And basically it now realign also with the desk. This is the same within an assistive framework. In this case, Paolo is holding the BCI, brain-computer interface, and within this, with this GUI, graphical user interface, that it is looking at, and with brain-computer interface, is giving some commands to the robot, and everything then is left to the task priority inverse kinematics with set base / inequality constraints. This RGBD is measuring in real time the position of the mouth of Paolo. And then everything is in real time. Also the object is located in real time. And then there is also, I mean, the estimation of the skeleton of another person. In this case is Daniele. Okay, objects are estimated in real time. This is quite easy. I mean, easy in the last years. It wasn't easy. I mean, 10, 15 years ago, but everything is fine, and the task can be accomplished. Okay. Okay, so now let us see a little bit some difference between task priority and weighted sum / behavioral control. So we will come back on behavioral control. So the example that I made is very stupid, but I hope is effective. If some of you hike or in countryside where there are also the car, or run, you know that there are two safety rules if you walk on a street where you do have also car. You have to take the curve from the external side, bends the curves, and you need to be with the car coming in front. Okay, those are the two safety rules if you run or hike or in a street where you have the car. Basically, this means that those two rules are compatible if you front a right-hand curves, okay? Because the two tells you to stay on the external side. But if you have a left hand curve, well, in one case you need to go in one place, in the other you need to go in the other place. Basically, with a task priority, you would definitely select one of the two, okay? But if you use a weighted sum or a behavioral weight normalization and whatever, weighted sum means that you are combining the two control objectives, and basically means that you are in the middle of the stream. Of course, you can decide to have the weight really unbalanced toward one or the other, but this means that you are assigning a priority. Okay, so we must pay attention when we look at a very fancy behavioral approach of mathematical what we are doing. Okay, there is also something that we need to notice here. Whatever is your control objective, there is a transition and there is a certain time window where you are in a transient. So you are not satisfying. You cannot do it instantaneously. This is mathematical. But there are several papers that allow you, help you in handling this transition. Now, the same that I've said with a very stupid running example is here from the thesis of Berlochet, is here with a robot. A weighted sum is a situation where you have two control objectives and you do not achieve any of the two. Here, with a task priority, you achieve one of the two and you go in the closest possible configuration to the other. So you minimize the errors to the other, okay? But this does not seem as dangerous as the previous one. I mean, if you implement it. So briefly, what is behavioral control? It's inverse kinematics, okay, with a different perspective. You have sensors and you ask movement to your robot, and you need to properly handle all those behaviors, all the outputs of the behaviors. If you don't do it properly, of course, something can happen. Historically, the very first approach is from Brooks, Rodney Brooks in '86. The subsumption architecture says that only one behavior is active at once. It was only, I mean, a first thought, I mean, it has evident drawbacks, but it was the first time that this idea came out, very, very interesting. And Rodney Brooks hold a blog where he talks about technology and future, autonomous car, whatever. I do suggest you to subscribe to the blog of Rodney Brooks, because he's a person with really a deep way to present, to think about stuff, and also a sharp way to write it down. It's not very polite, and I like it. Now, the architecture that we have seen earlier with the name Mood, but I mean, it's what has been proposed by Arkin in '89. So basically, you have some behaviors. Each behavior asks for some velocity, system velocity. You have a supervisor that assigns some weights, and somehow you sum, normalize, whatever, and you come out with only one. Somehow, this is defined as cooperative. It's a weighted sum, okay? More or less fancy, but it's a weighted sum. So let us see the different implementation of the subsumption, the cooperative, so the behavioral, let me say, and the task priority. Whatever kind of task priority, we have seen 3 different implementations of task priority. If I have, what is the simple robot? Is a point moving on a plane. This is the simplest robot that I can use to make this example. Move to goal. I want to go to a certain goal. I have an obstacle in my way. I want to avoid the obstacle. Move to goal. My control objective is a position, 2-dimensional. Desired is this one. And the Jacobian, well, it's the velocity. So it's the identity matrix, the Jacobian. And this is my inverse kinematics. Sorry, this is a K. It's not a lambda. Obstacle avoidance. I want to control the distance from the obstacle, so it's 1-dimensional, okay? And the Jacobian is a unit vector going from the center of the obstacle to the robot, because it's a material point, but it's a robot. Okay, and this is the null space project. Let us see the implementation of this. We have done it on the desk of my desk almost 20 years ago. This is the goal. This is the start, and this is the toy. It's a robot toy, really. I mean, it's now we have it on the wall of our lab. When I go close to the obstacle, I want to stay at this distance from the obstacle. So basically, in the first segment, I move, and I only have move to goal. So I go toward the obstacle. Then, the subsunction architecture says you have to have one behavior active at once. Now the obstacle avoidance. I implement obstacle avoidance, in this case with a minimum turn radius constraint, so that's the reason why I'm making this curve, but without, I would have a chattered here, and then I come back on the move to goal. Okay, this is the subsunction of competitive approach. This is the cooperative approach. So whenever you make a weighted sum, what is the problem? Is that in the second phase, you are summing the two control objectives. You have one velocity going to the goal and one velocity going to the radial distance to keep you on the red line. Depending on the relative value, you enter more or less in the disk. So you are not satisfying your control objective, okay? And this is what happened with a task priority. Because during this movement, the higher priority task is the distance from the obstacle. And any component of the lower priorities that would affect this control objective is filtered out by the null space projector. It means that you slide on the circle. Okay? So that's why task priority, I think, is more popular than whatever else, because you have a better control of your control objectives. You may also arrange the various tasks or behavior into actions. So you may define a library and a higher level of abstraction where you say a certain action, and the action will embed proper tasks in priority. And then your, let me say, higher level supervisor, your robot, select among the actions and don't take care anymore of the lower priority. And this is something that I think also Enrico will show. Let me skip some details about gain tuning. I think that with task priority is a little bit simple to tune the gains, personal experience, maybe not. And also I skip the stability analysis of those approaches. Very last, about kinematic control. I don't want to control the base and the arm with the same, let me say, weight. I need to, with a constant weight. Why? Because if my control objective is going out from the workspace, whatever is the relative weight, I always end with a manipulator stretch. And when my manipulator is stretched, I'm definitely in a kinematic singularity. So basically, the last detail is that I need to implement a strategy where I move the manipulator when a target is in workspace. I move the vehicle when approaching, and then the vehicle for large displacement without moving the manipulator. And basically, this is very, let me say, simple. It means that in the weighted, you need to balance the weight between the base. Here is 6 for an underwater vehicle, for example. You need to balance the weight between the base and the arm with a scalar that is decided based on another algorithm of decision making. But you need to do it. Otherwise, if your target goes out, you always have a manipulator that is in kinematic singularity. Or somehow you need to end. Okay? Okay. Let us move to the last part, the motion planning. It will be brief, so 15 minutes left, I think. Sorry? Sure. Well, we have a library for all these algorithms, but we also implemented the other libraries. So the group of Mansar released most of their software. We developed ours, but you can find several groups that release them. But the problem is the work to jump into their variable definitions and so on. This is the time that you need to do it. For example, MATLAB is very easy, but is not optimized. And then MATLAB does not give you control of what is done. I just used a singular configuration, and MATLAB didn't tell me an output a finite number. So I don't know what happened. So that's why basically most of the researchers, they implement their own code. Okay, we have seen up to now basically what, I mean, here too you can find several different nomenclature in the community, because robotics is a domain where several communities work together and they brings their terminologies. So basically here I use motion control, and in comparison with motion planning that I'm going to introduce now, but is not necessarily the only definition that you can find. But basically what we have seen here is motion control. It is local, is reactive. It means that at each sampling time, our mathematical problem was to find Q dot. Okay, this was our mathematical problem. It can run, it needs to run online in real time. It's easy, I mean, it's relatively easy. This is, let me say, deterministic. I know that QP has some iterative solution algorithms, but let me say that except for very singular cases, strange cases, let me say it's more or less easy. We have introduced also the constraints, and we can handle dynamic environment, basically the person entering into the scene. We can handle incremental maps, but it's just because it's in on time, but we can be trapped in local minimum. I'll show you very easily what is a local minimum for a local algorithm. Then, with the terms motion planning, we usually consider a global problem of finding the whole trajectory from the initial to the final time, okay? And this is usually done with random-based algorithms. So usually it's typically offline or in background. It's a 2 points boundary problem. For the one of you who has a mathematical background, you can appreciate that it's not easy. The more constraints I have, the more the computational time. If the environment is dynamic, I need to run it in background because my information are not good anymore. If the map is incremental, the same. But I can avoid the local minimum because it's a global solution. So what is the problem of local and global? Basically, I want to go from red to green, and basically I develop whatever planning algorithm I run is a segment. However, if I have a convex object and I only implement local algorithms, I can be trapped in a local minimum because I don't have global information and my algorithm is not running on global information. With a global motion planning, I can avoid easily and come out with a proper solution. Now, the problem is that if my environment is dynamic, up to a certain point, the solution still is incremental with respect to the previous one. But at a certain point, I need to change completely my movement with respect to what was the solution up to a few seconds ago. Okay? So basically, the point is that I need to run simultaneously local and global. Global in background, basically, and local in real time. So this is the kind of architecture we have implemented in our lab, but it's so generic that everyone is implementing. We do have in a high priority, high frequency, we have what we have seen up to now, task priority, for example, any kind of. This is running in real time. Then, in background, if your hardware, allowed to have multiprocessors or whatever, but in background, we run continuously a motion planning. What we do with our motion planning is that we plan in the Cartesian space. We also embed task priority such that the trajectory that is computed by the motion planning already satisfy all the safety constraints. And in this way, we afford the presence of dynamic environment, incremental map, and eventually the optimization. Everything we do is planned for a certain delta P ahead. So I need some time to plan. Obviously, I run in background, so in order to guarantee continuity, I plan with a certain window, not time window, but position window ahead, okay? If something happens here, I hit the obstacle. It's basically physics, so if not fast enough to think, I hit the obstacle. So this is basically the architecture. There are several details here, but of course, I'm skipping here. And I just want to finish with some videos about how to merge. Daniele was guest of Gregory Duque at McGill, the year where ICRA was run at non è Vancouver, Montreal. So now the first example are really trivial. It's a segment, of course. Everything here is static. Also the video is static. No. Static with obstacle also is very easy. Of course, here we are using Aruco to estimate the obstacle position. You see the tag over there. And now the planning is running in background, and taking into account the presence of obstacles. This was really the first. This is more or less the same, but I want to show you here. There is a graphic. Always Daniele in the lab, but now all the tasks that have been implemented are represented graphically as colored squares. Red, they are not active. Green, they are active. All the red are safety tasks. And the green are position, orientation, and effector. Here we have 7 degrees of freedom, not so much. So we are only in a space of 1 dimension. And while Daniele moves the tag, so the obstacles, the algorithms take into account the various control objectives. There is a joint limit and virtual wall on the top, obstacle avoidance on the bottom, and self-fit. Obstacle avoidance, there are so many because we want to control the elbow, the wrist, and there are several obstacles. So that's the reason why there are several. And here it's more or less the same, but with the face mask, because it's more recent, of Paolo. Okay, this is the same that we have seen with the priority level. Conceptually, it's the same. Just some strange movement of the robot and so on. The movement is a movement intentionally going from one part to the other of the robot so that it would eat itself. It needs to find, and without obstacle, it's very easy. It's just find a way to avoid hitting itself. Okay. Now, we just received the mail that this has been published yesterday in a transaction journal. Okay, this is a little bit boring, and it will be boring until the end. No surprise. Now the obstacles are running and the algorithm doesn't know what is the trajectory. So in this implementation, we are not using velocity information of the obstacles. It's only the current position. So every time that the motion planning works, it considers the obstacle static. And you have seen an emergency stop. The emergency stop is when the motion planning algorithm is not able to find an escape trajectory, and so it stops the robot. We know how much we need to stop the robot. That is less than the delta P that we need to compute a new trajectory. So that's why we have an emergency stop. So basically, the only situation where we have a hit is when the obstacle is going to the robot, but not the opposite. And then there are some real-time experiments, I think. You see that it changes in real time, the green line. Okay, so now they're not tagged anymore because the RGBD is estimating the skeleton of the person. Everything is real time. And so basically, Paolo is simply disturbing the movement after the movement starts in order to stress the replanning capacity of the robot. And this was an emergency state because the robot didn't have the time to replan the trajectory and decided to stop. Okay, aerial system is very stupid. Okay, this ends the lecture. Of course, I was only, the speaker of the results of the robotics community and the results of the young researchers of the lab. So let me thank all of them because my role was quite limited, and especially the youngest because they were the ones that spent most of the time in the lab to implement the algorithms. But together with the guys of the lab, also the two consortium we are part of. ISME is the consortium that Giovanni mentioned this morning. is a consortium of nine universities, Italian universities working on marine technologies. Of course, I didn't present anything of marine because this is a Industry 4.0 summer school, but a large part of our research is on marine robotics topic. And Prisma is another consortium with university from the south, basically on advanced industrial robotics. And those are the colleagues, I don't know if you know some of them. Francesca, she's there, so you can meet her. And yes, we need to redo the group pictures, obviously. Thank you for the attention. If you have questions, I'm here. So I will be here today and also tomorrow morning, and then I will make the tourist. Yes? I start planning from Delta P.
But in space, you do it from where you currently are.
See.
So when that emergency stop is when you don't have enough time.
Okay. Enjoy your lunch.